In this tutorial, we will learn how to do mediation analysis in R. So I'll quickly make an annotation here that is our focus, mediation analysis in R. And specifically, we're going to be using a path analysis framework. And please note that path analysis is a specific type of structural equation modeling, or SEM. So before we get started on this tutorial, if you haven't already checked out the tutorial on path analysis in R, I highly recommend that you do so, because we're really going to assume, since we're using the path analysis framework, that you're already familiar and comfortable with the concepts and techniques that pertain to path analysis, because this mediation analysis is just going to be an extension of that. Now, there are different ways in which we can conduct a mediation analysis, and the approach that we're going to use, as I mentioned, is using a path analysis framework. And specifically, there's different ways that we can estimate what's called the indirect effect, or in other words, whether or not there's a mediator or a mediating variable between a predictor variable and an outcome variable, and sometimes we call this an intervening variable. It helps sometimes to conceptualize what this actually looks like. And so I'll show you right here. We can actually display a mediation model using what's called a path diagram, which is typically done when we have a path analysis. It's just a visual depiction of the analysis model that we're specifying. So you can think conventionally we might have a predictor and an outcome variable. This would be a simple regression model here. And we could say that attitude predicts behavior here. And then we have the residual specified here. And so you note that here I have this, what's called the C path, which is conventional notation for a mediation analysis. And this is sometimes what's called just the direct effect here. Now, note that with a mediation analysis, we might specify a mediating variable or a mediator. And in this case, it's intention. So not only are we saying that attitude directly influences behavior, but attitude also influences behavior via or through intention. And so the path, in terms of the notation we typically use, the path that connects the predictor variable with the mediator, we typically label that as A. And the path that connects the mediator with the outcome variable, we typically label that as B. And you'll note that the direct effect pathway now has a prime next to it, so this is C prime. And this is to indicate that we're no longer just looking at the direct effect of attitude and behavior. We're also looking at whether attitude has an effect via other pathways on behavior, as well as whether behavior itself is predicted by another variable. So in other words, this is just kind of emphasizing to us that we're actually implementing statistical control here. The behavior is not just influenced by attitude, it's also influenced by intention too. And as we're specifying here, via intention via attitude, or rather the other way around, that attitude is influencing behavior via intention. Okay. Now the reason I bring up this notation here of A, B, and C prime is because this is what we're going to reference throughout the tutorial here. So tuck this away in the back of your mind. And also you might hear me using terms like exogenous versus endogenous variables. Now an exogenous variable is a variable in which there is no lines drawn to it. In other words, it's not predicted by another variable in the model. Okay? There's no arrow pointing to it. So attitude would be an example of an exogenous variable. An endogenous variable is any variable that has an arrow drawn to it. In other words, it's being predicted or specified to be predicted by another variable. So intention and behavior are both endogenous variables. And when we have endogenous variables, these are essentially outcome variables in their own right. And so therefore we specify the residual notation here. Okay? So this is the residual here for intention, and this is the residual for behavior. Okay, so just to quickly sum up here, we have our predictor, our mediator, and our outcome. And this is a fairly generic mediation model here. And if you want to think about this in terms of regression equations or just standard regression notation, this is how you could think of it right here. So we essentially are specifying three different regression models here, specifically linear regression models. And you can just think of path analysis as being an extension of our general linear analysis, our linear regression that you've learned in other tutorials, such as multiple linear regression and simple linear regression. Okay? And so the other thing I want to note too is that you can specify what's called a complete mediation model or a partial mediation model. Okay? So with a complete mediation model, we're actually saying that the effect of attitude on behavior is completely mediated by intention, meaning that once we throw intention into this model, this path right here, the C prime path, the direct effect, goes to 0, that it's non-significant. There's no direct effect of attitude and behavior when we account for the mediator of intention. Okay, so this is typically how we'd specify there. This is a fairly strict assumption here, and often we do see some association between the predictor and the outcome variable, even when we have a mediator presence. So what we're going to be focusing on today is what's called a partial mediation model, where we are specifying a mediator, but we're also saying that we do have some reason to believe that there will still be some effect of our predictor on our outcome variable, so the C prime path is still specified there. Okay, so that gives you a little bit of background here. Now, in terms of how we're going to estimate the indirect effect, and so the indirect effect is going to be that effect of the predictor variable on the outcome variable via our mediator variable. So we say instead of a direct effect, that's an indirect effect. We are going to use what's called the product of coefficients approach. And there's different approaches you could use, but the product of coefficients approach is really one of the more conventional ones that we seeing used today, and there's different ways that we can actually implement this. And so I'll note that we can use a Sobel test, which is a specific type implementation of the delta method, and this is something we'll be learning today how to apply. And the delta method is fairly conventional, but it does assume that the sampling distribution of our indirect effect that we're estimating is going to be normally distributed, which is not an assumption that can be easily met in most circumstances when it comes to an indirect effect. Also, the delta method, I should note, also shows some bias in small sample sizes. So that's something to consider as well. Now, there's also different approaches we can use, which are resampling methods. And these are methods we can also use for estimating for the product of coefficients approach and estimating that indirect effect and its level of statistical significance. So a very common implementation of the resampling method is bootstrapping. And that's what we're going to be learning today. And there's various types of bootstrapping. You could have percentile-based bootstrapping. You can have bias-corrected. And you can have bias-corrected and accelerated as its own form. And we're going to be focusing, though, on implementing percentile bootstrapping, as there's more evidence to suggest that this is one of the better approaches when using bootstrapping to estimate an indirect effect. Now, like the delta method, there does tend to be more bias in the estimation when it comes to applying bootstrapping techniques to small sample sizes. So let's say sample sizes that are less than 80 people or so, or 80 cases, depending on what your unit of measure is. Okay? But the big benefit of these resampling methods is you don't have to assume that the indirect effect, that its sampling distribution is normally distributed. Okay? And that's an important thing to consider. So I'll show you how to do both a Sobel test, which is again a specific implementation of the delta method, and I'll show you how to do a resampling method and specifically percentile-based bootstrapping. But just note that the percentile-based bootstrapping, although it can take a little bit more time to estimate the model, when we are doing bootstrapping, it tends to give us more accurate estimates of that indirect effect as well as the associated standard errors and statistical significance. Okay? All right, now in terms of the statistical assumptions, we won't go through those in this video. Just check out the path analysis in our tutorial. That goes over the statistical assumptions, and they're going to be the same statistical assumptions because we're just using a path analysis framework here to do our mediation analysis. Okay, so with that, let's get into it. So let's do some preliminary steps here. And so the first thing we're going to do is we're going to read in our data. And so I'm going to note that we're reading in the data. And in this case, we're going to be using the reader package rather from the tidyverse of packages. And so it's just using the library function reader here in the parentheses as a sole argument. Click run there. Okay, we've accessed that. Now, if you haven't installed Reader recently or you need to update it, make sure that you do the installed packages with Reader in parentheses within within quotation marks within the parentheses in order to install or update that package. Okay, so if you haven't done that already. Okay, so the next thing we're going to do is we are going to set our working directory. And I'm going to use the setwd function. I know that my working directory is going to be my H drive, and it is going to be my R workshop folder. This is where the data file we're going to be accessing lives. So I'm going to run that, specify that where my working directory should be set. And I'm actually going to move this above the reading in the data, because really I should be specifying that working directory before I read in the data. And so as I mentioned before, I've now accessed the reader package, READR, and now I need to use the read_CSV function to read in the data for this tutorial. Okay, and so I'm going to call this data frame that we're going to read in. I'm going to call this just DF or data frame, just for short. That's completely arbitrary, and I'm using the left-handed arrow operator to specify that I'm going to be doing variable assignment here. I'm going to be naming this data frame that we're reading in as an object that I can later reference here. And so I'm going to apply the read._CSV function from the reader package. And within the parentheses and within quotation marks, I'm going to specify the name of the data file here, which is planned behavior.csv. Okay, so planned behavior.csv is the name of the data file that we're going to read in. And it's a capital P and a capital B, no spaces. So let's go ahead and run that. Okay, so as you can see, if I go to the global environment here and click on that data frame, I've got the following variables here. I've got attitude, norms, control, intention, and behavior. We're only going to be focusing on attitude, intention, and behavior because we want to bring to life this model here. So attitude, intention, and behavior. Just note that here the variables are all lowercase in terms of how they're written, okay? Because R is case and space sensitive. All right, so we have the data read in here. Sometimes it's good to just do a quick read, and you can see the reader function does this automatically. These are numeric in terms of the how the variable types, but we can also do str with our data frame object in the parentheses, and we can run that, and we can get a little bit more information. And so yeah, we can see our variables are a type of numeric, which is good. That's kind of, it makes it easiest to work with when we don't have to change the variable types for any of these variables in order to run our mediation analyses here. They're all quantitative, they're all numeric in nature, okay? All right, and it doesn't really matter what the scales are here. We're more interested in just the effects in terms of what the sign or direction of the effect is and whether or not it's statistically significant, okay? All right, well, the next thing that we're gonna do is we are going to specify our path analysis model, okay? This is going to be the basis for our mediation analysis. And so we're going to be using specifically a package called the Lavon package. And this is a package that's great for implementing structural equation modeling, or SEM, where path analysis is a specific application of structural equation modeling, okay? And so if you haven't already, make sure you do install.packages with Lavon in quotation marks within the parentheses, and install or update the Lavon package if you haven't done so recently. I'm going to go ahead and just use the library function and Lavon, which you would need to do anyway, just to access it, because I know that I recently installed and updated this package. So go ahead and click run. And note that you'll get a little bit of warning here. Lavon is still in its beta version here. And so that's just something to note, that it hasn't quite reached version 1 yet. And so it's been in beta for a number of years, but this is pretty conventional package by now. A lot of people use this for structural equation modeling and path analysis. Okay, so the next thing that we're going to do is we're actually going to specify our model, and we're going to be using the Lavon notation. Okay, and so first we need to name our model, and this is similar to what we would do with any regression model if we were using the LM function from base R to specify a linear model, for example. We'll just come up with some arbitrary name. Here I'm just going to call it spec mod for specified model, and I use the left-handed arrow operator to say, what am I going to assign to this object here? And this is where we specify our model all in quotation marks. I'm going to spread this out over some lines and add in some notation so this is a little bit clearer. And just make sure that your model that you're specified is preceded by a quotation mark and ends with a quotation mark as well. Okay, so the first thing I'm going to do is I am going to make a little note here saying that I'm going to specify the C prime path here, which is our direct effect. Okay, so just as a quick reminder, this is what I'm specifying here first, is the attitude to behavior link, so the C prime pathway. Okay, and below this, I'm going to specify that model. And so remember, our outcome is behavior. Okay, and then we use the tilde here, just like we would with other regression-based functions, or most of them in R, to specify that we're regressing this outcome variable called behavior, which is all lowercase, onto a predictor variable, which is going to be attitude. So again, behavior regress onto attitude, that's our C prime path. But we're actually going to do something a little bit different here, as opposed to just putting attitude, behavior regressed onto attitude. We're going to add we're actually going to make a specification here to actually label this pathway so we can reference this pathway later to actually do that product of coefficients approach and to estimate, apply both the Sobel model or the Sobel test approach to product of coefficients that I mentioned above, as well as the percentile-based bootstrapping, which is a resampling method that we can use as well. And so what I'm going to do here is, because I noted that this is the C pathway, I am going to put the letter C with an asterisk here. And so you could put whatever you want here. This is anything you precede the asterisk with is just whatever you want to label it as. And so here I'm putting C. I don't want to put prime here because that would throw things off, because that would be interpreted as a quotation mark or an apostrophe. So I'm just going to put C here, but just know that that implies C prime. Okay, and so we're going to label this pathway. So we're saying attitude predicting behavior, or in other words, behavior regressed on attitude, is the C pathway. Okay. Now, the next thing we're going to do is we are going to specify, and I'll make a note here, path A. Okay, and so if you remember, path A is this path from our predictor variable to our mediator, which in this case is attitude to intention. So this is our A pathway. So in other words, it's going to be intention regressed on attitude. Okay, and so that's what we're going to specify here, is intention regressed onto attitude. Okay, and we're going to do the same thing. I'm going to put A asterisk, and A asterisk is going to specify now that we can reference this later and say that this pathway is the A pathway. Okay. Next, I'm going to specify or make an annotation that I'm going to estimate the B pathway, which, just flipping back here quickly, the B pathway is the pathway between our mediator and our outcome here. We label this B, or in other words, it's the path where we regress our outcome of behavior onto our mediator of intention. Okay? And so I'm going to regress that outcome of behavior onto the mediator of intention. But again, I'm going to use the asterisk notation here to note that this is the B pathway. Again, you'll see why this is actually going to be referenced later, and you'll see why in a second, why this is important to do. Okay? And so let's get to that point here. So now let's specify the indirect effect here. Okay? So this is so that we can explicitly estimate the indirect effect. And I'll make a little notation here in the parentheses that when we're specifying the product of coefficients approach, it's literally what the name implies, product of coefficients. It's the A coefficient, A pathway, times the B pathway. In other words, the coefficient for the A pathway times the coefficient for the B pathway. So we're just multiplying these two estimates together, A times B, and that's the product of coefficients there. Okay, and so the way that we specify this in the Lavon notation is we can put whatever we want here to call it. I'm just going to call this AB, okay, to have some object name that we can reference, and this will appear in the output that we receive from this. And then you're going to do a notation that's colon equals, okay? And so this is how you specify these additional parameters or estimates in your model using Lavon notation. So the name of it, followed by colon equals, and then actually literally spell out A times B. So we're multiplying the A pathway coefficient times the B pathway, and we're going to see, after estimating that and its standard error, whether or not it's statistically significant. So this is the Sobel test right here. This is what we're specifying here is the Sobel test, in other words. Okay? And then, as I said, you finish up the model with a specification here, and its specification with the ending quotation marks. And so we can run this whole chunk here. And so now you'll see that we have all the values assigned to spec mod there. And now we can reference it in the next step, which is when we actually estimate the model, okay? So we've specified the model, and now we get to estimate it. And so what we're going to do is we want to be able to reference the model estimations and summarize them in a subsequent step. So I'm going to create an object that I call fitMod. This is completely arbitrary here. You could call it whatever you want, but I think fitModel is what I would like to call it because that's what we're doing here. And we're going to use the SEM function from the Lavon package. And so that stands for structural equation modeling. And the reason that we're using this is because, again, path analysis is a specific application or implementation of structural equation modeling, which is called SEM for short. Note it's just all lowercase SEM. So as the first argument, we're going to include the name of the model that we specified above. Okay, so specmod. So that's going to be one of our inputs. And then our second input or second argument is going to be data equals df. And this is our name of our data frame. Remember, we read in our data and called it df. So we're saying apply, essentially estimate this model we've specified, or in other words, fit this model we've specified here that we call specmod to the data, which is df here, okay? All right, and so we can click run there. You'll note that nothing happens because we've just assigned this to the to an object. We haven't done anything with it yet, and that's where the next step comes into play. And I'll make a little note here just so this is where we fit or estimate the model. And then the next thing that we're going to do is we are going to summarize the results or output, okay? And so this is where we're going to use the summary function, which comes from base R. You might be familiar with it already from using linear models and other functions that the LM function that you often summarize the output or results using the summary function. It's all lowercase. And as the first argument, we're going to type in the model that we just fit here. Okay, so all the information we just fit, it's going to be implemented as the first argument. The second argument, we're going to do fit.measures equals true. And that's saying that we'd like the fit indices or fit measures that tell us how well our model fit the data. Now in this case, we have a just identified model, which simply means, and refer back to the path analysis in our tutorial for more information on what just identified, under identified, and over identified models mean. But just identified means that we have 0 degrees of freedom. And so this means that our model is going to perfectly fit the data, okay? Because there's no degrees of freedom here. All right, so, but still it's good to request this in case if you were to do a partial mediation model where you did not specify that path between behavior and attitude, or rather from attitude to behavior, that C path, then you would have a model in which the fit measures would be a little bit more applicable, or would be a lot more applicable there, okay? But for the time being, we'll request them anyway. And so we'll get those in the output. And then we're also going to request the R square values to be included in the output as well. It's just R square equals true. All right, so let's click run here and let's check out our output. Okay, so we see that Lavon ended normally after 11 iterations. Okay, so that's good. We found a solution to the model here. As I mentioned before, there's 0 degrees of freedom to this model, so this is just identified. So we don't need to proceed forward and interpret any of these fit indices. If you did have more than 0 degrees of freedom, then you would come down here and you would want to interpret these model fit indices and determine whether or not the model has adequate fit to the data before you proceed forward with interpreting the parameter estimates. Okay? And note that the number of observations is 199. In this case, it's 199 people within this organization from which we have data on these variables. Okay? All right, so the next thing that we're going to do, since we have a just identified models, we're going to come down here to the parameter estimates section, and specifically below that to the regressions, because that's all, again, we're looking at here really are these regressions within our models, the pathways, the linear estimates for each one of these pathways here. And you can see that our notation appears here in parentheses. So remember, we specified the A path, the B path, and the C path. And so if you look through here, you can get this is the unstandardized regression coefficient or weight or estimate, however you want to call it. And you get its associated p-value here, and the standard error and z-value are also pictured. And so you can see that the C pathway is not significant, okay? P-value is equal to or greater than 0.05, but we can see that both the A pathway and the B pathway are statistically significant here and positive, okay? So what does that mean? It means that we find that or the association between attitudes and intention is more positive, and is positive in nature and statistically significant. So that A path is statistically significant, and the path between intention and behavior, which is the B path, is also positive and statistically significant. Okay, and here you get variance estimates as well. These are the residual variances because remember, again, for intention and behavior, these are endogenous variables, and these are outcome variables in their own right. Since there's arrows drawn to them, there's variables that are predicting them, and so we estimate residual variance as well. Okay, and then also because we have two outcomes in this model, or even though we refer to intention as a mediator, it is technically an outcome, and it is an endogenous variable, just like behavior, because it does have it does have an arrow drawn to it. In other words, another variable, at least one variable, is predicting it. We also get an R squared for it too, the amount of variance explained, or the proportion of variance explained. So here the R squared for both behavior and intention. But what we really came here is our defined parameters. Okay, so remember how above we specified this parameter here, we defined it, which we said was A times B. Well, this is the estimate here. Okay, so this is the estimate of A times B here. Okay. And so you can see that if we, A times B, and you can actually watch as a basic calculator. So if you look, A times B in terms of our output is 0.484 and 438. If we multiply those two values together, just using R as a simple calculator, so 0.484 times 0.438. So again, just taking this value times this value, should be close to this. So there's some rounding differences here, but you can see it's essentially 0.212 if we round. Okay, so that's literally the product of coefficients. That's how we get to this estimate of the indirect effect. So it's the effect of attitude on behavior via intention. Okay, so this intention is the mediator or intervening variable, and if we find a significant indirect effect, we often say, okay, there's a significant mediation here. All right. Now the question though, is this indirect effect of 0.212 that is positive, is it statistically significant? And here we see the p-value is less than 0.05, so in a conventional sense, we would say that this estimate here, this indirect effect estimate, is statistically significant and positive. Okay, so here we found evidence of a significant indirect effect, and therefore evidence of a mediator, and specifically the mediator being intention, which is mediating the effect of attitude on behavior. Okay. All right. So that's the first step. Okay. So coming up here, I want to note right here too that I'll make an added note here that this is the Sobel test that we're doing. Okay. And so in other words, this is our delta method. And just to make that clear, so we've now specified a model, we've done the Sobel test. It's fairly quick and easy to do the Sobel test, and it's pretty good. It's just that remember the Sobel test and the delta method in general suffers from the shortcoming that it assumes the sampling distribution of our indirect effect, okay, this product of coefficients here, is normally distributed when often that is not the case. When we multiply two coefficients like this, we don't necessarily get a normal distribution in terms of the sampling distribution, okay? And so that's why we're now going to do an extension of this. We're going to use the resampling method and specifically percentile bootstrapping, okay? And this will not assume that the indirect effect and its sampling distribution are normal, okay? And so what we're going to do is we're going to use the same model we just specified before, okay? And so I'm just going to copy and paste this. You don't necessarily need to do this. I just want to make this clear what we're actually doing here. And so what I'm going to do is I'm going to take this same specified model, okay? Because it's the same thing as we were doing before, okay? So I won't review all this, but it's the exact same model specification before. Now we're just going to tweak a few things and apply a different function to it to run the percentile bootstrapping, okay? And so the first thing we want to do when you have bootstrapping, it's important to specify or to set what we call a seed to ensure that you can replicate in the future. That essentially it's a random value that you're assigning to it to make sure that each time you run this, because it does involve these random draws from our sample when we're doing bootstrapping, we need to make sure, if we want to be able to replicate and reproduce this at different times, that we set a seed so that we can recreate our steps, okay? And so we're going to use the set.seed function, which is from base R, and you can put any numeric value you want as your seed. I'm just going to put 2019 here. It's arbitrary. You can put whatever number you want here. And the important thing is that you want to run this before you then fit your model or estimate your model. And this way you can reproduce it each time to the same and get the exact same results. Okay. All right. So I'm going to run that line there. And also, I'll also run, we don't need to do this, but just to emphasize this, I'm just going to rerun the spec mod. We haven't changed it or anything like that. The same values are applied to it. But this just emphasizes that if you're going to be doing the percentile-based approach and you're not just doing the direct Sobel test, the delta method ahead of time, you would definitely need to specify and run this before you start actually fitting the model or getting estimates for the model. Okay, and I'm just going to run this set.seed again, just to emphasize this is the typical order of operations we would use. Okay, so the next thing I'm going to do is I'm going to specify, I'm going to name an object that I can assign our fitted model data to. And so instead of fit mod, I'm going to add just a 2 to this. So now our object is fit mod 2, which differs from the initial model we specified here when we were just interested in applying the delta method and specifically the Sobel test. And so I'm going to do the left-handed arrow operator here. Again, we're going to use the SEM function from the Lavon package. SEM, all lowercase, stands for structural equation modeling. Our first argument is going to be the same as we did before. It's just spec mod, the name of the model we have specified here. Okay, so all the pathways we specified. The next thing we want to do, though, is going to be a little bit different. We're going to do CI, and this stands for confidence interval, so it's lowercase c and I. So CI equals true, saying we want the confidence intervals, and then we need to say what level of confidence interval do we want. So we do level equals 0.95, okay, 0.95, and this is saying we want 95% confidence intervals, okay? And this is how we're going to determine whether or not the indirect effect is statistically significant. If the 95% confidence interval, if the lower and the upper limit does not include 0, then we consider it to be statistically significant, okay? And then the next thing I'm going to do is apply boot.ci.type equals pers in quotation marks. So this is saying the bootstrapping confidence interval type is percentile. So perc, however you want to pronounce PERC for percentile, all lowercase, and make sure you put that in quotation marks there, okay? All right, so the next thing we're going to do is, oh, and I forgot, very important part, is we also need to specify, I'm going to do this on a separate line here, bootstrapping, how many iterations or resamples do we want? And it's fairly conventional to do 5,000 or so, okay? For the sake of time here, because if you run 5,000, this is one of the challenges with bootstrapping. It's gotten so much better with computational power, but it can still take quite a long time to run 5,000 bootstraps. I'm going to do something a little bit less aggressive than that, but just note that 5,000 is fairly conventional. Do at least 2,000. 5,000 is typically better when you're running this and there's actually stakes behind this, okay? And oh, I'm sorry, I actually got ahead of myself here. I got a little bit ahead in terms of the type of bootstrapping here. So actually, this is actually going to go down to a separate function. So I'm going to save this for later down here, okay? I was getting ahead of myself to the parameter estimates function we're going to run after this. But okay, so back here to and I see I've also misspelled bootstrap there. So making all sorts of mistakes here. So, okay, so back to fitting this model. First argument is going to be spec mod. That's the model specification here. Second argument is data equals, and this is just where we're specifying the data that we're going to fit this model to, which is our DF data frame. Okay, that should look familiar. And the next thing that we're going to do is we are going to do SE, which stands for standard errors, okay, equals bootstrap. Okay, so the standard errors, we want those to be bootstrap standard errors. And again, I'm just going to do 100 bootstraps here, or resamples. I would really recommend when you actually do run this to do like at least 2,000, but 5,000 is fairly conventional. It just will take a while, okay? And it could take longer depending on how powerful your machine is, okay? So let's go ahead and run this here. And so this could take a moment. So you'll notice the stop sign will pop up, okay? We only did 100 here, so this is gonna be pretty quick, so that's nice. But just note, again, it could take longer if you were to actually put 5,000 here for the number of resamples. Okay, so now we're going to use all this information that I got ahead of myself and used. So what we're going to do is we're going to apply a function from Lavon that's called parameter estimates, okay? And note that it's parameter estimates, but the E is capitalized in estimates here, okay? And the first argument is going to be fit mod 2. So we're going to reference the model we just fit here to the data and all that information. And then here, I'm going to copy and paste in what I already specified above. So confidence interval, CI equals true. We want to estimate the confidence interval. The level of the confidence interval is 0.95, which specifies 95% confidence interval. The boot.ci.type bootstrap confidence interval type is percentile, and that's abbreviated as PERC, all lowercase, and put that in quotation marks. And we should be ready to go here. So now we're going to actually get the parameter estimates here for our bootstrapping. Okay. All right. So what you will see here is we get the bootstrap confidence intervals, and you'll see those represented here by CI.lower. This is the lower limit of your 95% confidence interval, and here's your upper limit here in the next column. And really what we're interested in here is just skipping down to our AB parameter definition, which is that product of coefficients, this is just estimating A times B here as we did before, except now we're going to see if the confidence interval here, the 95% confidence interval, includes 0. We can see both the lower limit and upper limit are both positive, and they do not include 0, so this would be an indication that this is statistically significant, okay? So just make sure to look towards the lower and upper confidence intervals here. This is still your point estimate of your product and coefficients. This will be the same regardless of whether or not you do the Sobel test or you do this resampling method approach of percentile bootstrapping. But the significance, be sure to look at the lower and upper confidence interval limits here, okay? So this indicates that, again, this is just a more robust way of testing whether or not we have an indirect effect here, and it appears we do. And again, that indirect effect is the effect of attitude on behavior via intention. And so it appears that intention is a significant mediator here, okay? And now you might be saying, well, what about all the, fit information and so forth? Like, what if I had a model in which I had more than 0 degrees of freedom in it? Well, if you want to estimate the model fit, you would just go up here and just put fit mod 2. Okay, so summary, we already applied that before, but this time to the second model here, which is fit mod 2. Run that, and here's where you'll get all that information. Okay, and you'll see that, and we would want to also, if you want the fit measures and so forth, you do fit measures equals true. And let's say we also want R square like we found before, you just put that there. And this is exactly what we did above here. So fit measures equals true, R squared equals true for our summary function. So I'll just rerun that. Oops. Well, now I've done the bootstraps again. And now we'll run that summary function. Okay, so now you get all the fit indices and so forth and all that information here, and it'll tell you how many bootstraps and so forth were run, all that kind of stuff, okay? So just the important thing to remember, after you specify your model, if you're using the percentile bootstrapping approach, you want to set your seed. You can put whatever value you want in there. Then you're going to fit the model to the data, okay? The model that you specified to the data that they correspond to, or that the model corresponds to, and make sure that you set it to bootstrap and that you set the number of resamples or iterations. Specify the name of that model by, or name it using the left-handed arrow operator. And then to get the fit information, and if you want basic information to reiterate the bootstraps that were actually estimated, you're going to use the summary function from base R with the name of the model you just fit there and named. And then fit measures equals true, r squared equals true. Those are typical arguments we'd request. But in order to actually do and get the percentile-based bootstrapping estimates of the indirect effect, use that parameter estimates function with a capital E for estimates from Lavon. Put the name of the object that we fit mod 2 as the first argument. Specify you want confidence intervals by CI equals true, the level of the confidence intervals, 0.95 for 95% confidence intervals, and boot.ci.type equals perc for percentile bootstrapping. Okay? And so that's how we do it. So this is how we would do both a estimated indirect effect using a path analysis framework to detect whether or not there's a mediator. In other words, to conduct a mediator analysis. And we can estimate that indirect effect using the delta method and specifically the Sobel test, or we can use a resampling method such as bootstrapping. And here we applied the percentile bootstrapping approach, which tends to be recommended today. And we work through everything. Again, if you need some review on path analysis in general, check out the Path Analysis in R tutorial. Otherwise, I hope that you found this mediation analysis in R tutorial to be helpful. Thank you.